Good morning. Today we're going to talk about solving quadratic equations that come in a form of a special case. And so these are typically a little bit easier to solve. So we're going to start with those. I wanted to first differentiate between two things that you're asked to do commonly in algebra. The first of which is lots of times you're asked to factor things. And when we factor things, we are basically just breaking a product up into two or more terms that were used to multiply to create that product. When we're solving, we are actually finding an answer or a solution. And solving only applies to equations, right? So we only solve equations. We do not solve expressions. And so I want to take a moment and just identify what are some of the differences, different ways that we see factoring versus solving. So there are obviously, I can only factor an expression because there's no equal sign. And if there's no equal sign, I can't solve it. There are some things that we can't factor. We've learned that the quadratic formula is used to help us solve things that can't be factored. We've also learned that if you remember back to Algebra 1, we learned that you take the square root of a number and that would help us solve equations. And then finally, we learned how to use completing the square in Algebra 1, and we will recover that again in Algebra 2. And completing the square, it does not give you factors, it gives you solutions. But there are lots of things that can be factored and solved. And one of those things is we used grouping, which was perhaps you learned a box method or a grouping method. And that's where we break something into two discernible groups or factors. The other thing we learned how to do is use the greatest common factor. My space isn't big enough. And when using GCF, lots of times we would end up with 2 times x plus 6. And these are two factors. And what we did is perhaps started with 2x plus 16, and we factored out the largest common factor. And then lastly, the other one we do is difference of squares. And that would go in the center also. And we have abbreviations for these. Lots of times you'll hear difference of squares referred to as dots. You'll hear greatest common factor referred to as GCF. Grouping, factoring, box method, all of those are ways that I can both factor if I'm asked to, or I can factor and then solve if I need to. All right, so let's look at how to factor using greatest common factor, because that's a little bit interesting. And this is typically one that is pretty easy to wrap your head around. There are some discernible steps that we want to go through when solving or factoring using GCF. The first thing we want to do is, since we are solving, right? Since we're solving, we want to set our equation equal to 0. Because if you think back to what it means to solve, when we are solving a quadratic equation, we're trying to find the x-intercepts, the roots, the zeros, the solutions, the place where that parabola crosses the x-axis. The parabola will cross the x-axis when the y value is equal to 0. So then the next thing we're going to do is we're going to look for the greatest common factor. You don't have to look for the greatest, but if you will, it'll save you steps. You're looking for a number that is common to both the coefficients a, b, and the constant c. And it is helpful because you only have to do it once if you find the greatest common factor. If you don't find the greatest common factor, you just find a factor, then it's possible that you would have to factor it twice. This can be a number or a variable, or it actually could be both. So your GCF can be variables, numbers, or both. The third thing we do is we are going to divide all of the parts of our equation by the GCF. Once we have done that division, we're going to factor further if I need to. Hopefully we won't need to. And then once I have it fully factored, I set each factor equal to 0 to find out what the different intercepts are. And sometimes there will only be one factor. Sometimes there will be 2 or 3 or even 4. We'll look into that later in the year. Let's do some equations, or let's factor some equations and solve them if we need to using these steps. So the first thing I notice is number 1 does not ask me to solve. There is no equal sign. In example number 1, I am just factoring, right? So I want to go ahead and just identify that we are factoring. I need to figure out what is the greatest common factor. First thing I notice is that the last term does not have a variable, so x cannot be a common factor. But I also notice that all of these numbers are divisible by 2. I'm going to identify my GCF as being 2. Right? That was step number 2 up here. The next thing I'm going to do is I'm going to divide all my terms by my GCF. When I do this, I can now simplify. Remember, always remember, 2 is a factor. That is one of our factors. What the other factor would be is the result of this division. So 4x squared divided by 2 is 2x squared. Negative 12x divided by 2 is negative 6x. And positive 2 divided by 2 is a positive 1. All right, so that's step number 3. Step number 4 says, look at these two factors and determine if they can be factored further. So I would look at this trinomial and I would ask myself, are there factors of 2 times 1? I'm sorry, yes, are there factors of 2 times 1 that would add up to negative 6? And the answer in this case is no. So this is fully factored. I can't solve. And this would be my factorization. Let's look at number 2 next. In number 2, the first thing I want to do is set my equation equal to 0, and it is not already that way. So I'm just going to subtract 15x from both sides. And I end up with 3x squared minus 15x equals 0. My next step is to identify my GCF. And in this, I notice both of them have x's. So x, the variable x, will be part of my GCF, and they're both divisible by 3. So I'm going to divide all parts of my equation by 3x, remembering that 3x is one of my factors. The other factor is what remains inside the parentheses after I do that division. 3x squared divided by 3x is simply x. Negative 5x divided by 3x is negative 5. 0 divided by anything is just 0. From here, I have factors. These are factors. But I haven't solved it yet. To solve, I'm going to need to do step 5, which is to set each one equal to 0 and solve what I call baby equations. Anything divided by 0 is just 0. And if I add 5 to both sides here, I end up with x equals 5. These are my 2 solutions. So I'm going to. And if I wanted to think about them graphically, one side of my parabola is going to go through the point 0, 0. The other side of my parabola is going to go through the point 5, 0. Kind of scrunched him together there. These are the 2 roots, the zeros, the solutions, the x-intercepts for this quadratic function. Let's do one more. This one is already set to equal to 0. So I have saved myself that step. My GCF in this case, they both have x's and they're both divisible by 2. So I'm going to say that my GCF is 2x. I'm going to divide all my parts by 2x. And I'm going to remember that 2x is one of my factors. And when I do this division, my result is 2x times x plus 4. Step number 5 suggests that I set each factor equal to 0 and create and solve my baby fractions. If I were to write these as x-intercepts, again, I would have 0, 0, and I would have -4, 0. If I wanted to sketch what that looks like, that means my graph goes through 2 points that would look something like this. All right, that's enough of GCF. Let's see what other ways we have for factoring. All right, let's look at a different way that we can factor and solve special cases. In this case, the special case that I'm looking at is called a difference of two squares. I am looking for patterns when I look at these. The first thing I notice is that all of the examples that we are solving today, and in fact, all of the examples or problems that you could do using difference of two squares have two terms. So I need to recognize what the pattern is to use this technique. And you can also use just a general grouping technique, remembering that because there is no bx term, that just means that it's a 0. So you could also think of this example, 25x squared plus 0x plus, minus 9. You can use your traditional grouping to factor this as well, but sometimes it's a little bit faster if you can recognize what some of the patterns are. So let's look at this. In this particular case, a difference of two squares, it can be recognized when there is a perfect square a variable that's being squared, a subtraction symbol, and another perfect square. So key things here, this has to be subtraction. It has to be a difference. And the other thing to note is that these two, A and C, must be perfect squares. Okay, so if those two things exist, then we can use a pattern to solve this. And essentially what the pattern boils down to is I'm going to take the square root of the first term, and I'm going to put him at the beginning of the parentheses. I'm going to take the square root of my variable and put him after my first constant. And then I'm going to have two factors that with different signs. I think of difference of two squares will have different signs in my factors. And then lastly, I take the square root of my C term. And he will go at the end of each grouping symbol. Once I have it factored, I'm going to set each factor equal to 0, and then I'm going to solve my baby fractions. So let's look at an example. The first thing I like to do is just identify, is 25 a perfect square? Yes. Is 9 a perfect square? Yes. Is it a difference? Yes. So this is a difference of two squares. If I want to think about what's the square root of 25x squared, that would be 5x. If I want to think about what's the square root of 9, that would be 3. And that's the heavy lifting in this strategy. I know that the first root goes at the beginning of two grouping symbols. I talked earlier about how my two factors will have different signs. And then I take the square root of my C term, and that goes at the end of my grouping symbol. And that is everything I need to do in order to group this. Factor this. Notice this says factor. So once I've done this step, I'm done. I don't need to set it equal to 0 or solve baby equations because I was only asked to factor. There is no equal sign. For the next one, I need to first put it in standard form. I would write it as 4x squared minus 25 equals 0. I ask myself, is 4x squared a perfect square? And it is. The square root of that would be 2x. Is it a difference? Yes. And is 25 a perfect square? The answer is yes. So I can use difference of two squares to factor this quadratic. I put the first set of roots at the beginning of my parentheses. I use different signs, and it doesn't matter whether you put the subtraction or the addition first. And then I take the square root of my C term, and he goes at the end of my grouping symbols. And all of this is set equal to 0 because I'm asked to solve. There is an equal sign, so this is a necessary step. From here, I set each factor equal to 0. These are my baby equations. And I solve each one to x equals -5, x equals -5 halves. Again, please leave your answers in simplified fraction form. They are easier to communicate with. These are my two solutions. Notice that they have the same number, different signs, and that will often be the case when using difference of squares. So I'm going to choose green here. These are my two solutions. And if I wanted to think about them as x-intercepts, it would be -5 halves, 0, and +5 halves, 0. And those are the places where my parabola crosses the x-axis. All right, folks, I'm actually going to skip number 3. I think you can do that. The answers to that are online in the answer key, the notes key for the, I think you get the idea, I hope. I wanted to just real quick before we leave, just talk about some general steps when you are asked to solve a quadratic equation. It is always, always easiest if you look for a GCF first. Just make the number smaller, if nothing else. Then ask yourself, can I use difference of two squares, or can I use a square root if applicable? That will be easier than trying to do full grouping. If possible, if I have a trinomial, then use your grouping to solve it, because I guarantee you'll make fewer mistakes and it will be less time intensive than our only other option, which is to solve with a quadratic formula. This is considered an equation that is prime, doesn't have real solutions, and it is sort of the method I use as last resort. That's it on solving the simple cases, folks. Look forward to reviewing how to solve trinomials next class.